Kinetic molecular theory is the simplest model that does a decent job of explaining the behavior of gases. In this model, we look at a gas as being a collection of particles. Those could be molecules or atoms, depending. And those particles are in constant motion. So here we have an illustration. These gas particles are moving. They're going to move in straight lines until they run into something, and then they're going to crash and bounce back. The collisions are going to be elastic collisions, so they're not going to slow down. They're just going to keep bouncing around, kind of like a game of Pong. You guys know what Pong was? Yeah, at least it's like the original computer game, right? There was this little blip, and it would travel around, and you had a paddle, and you had to try to keep it going, right? It didn't slow down because it wasn't real, right? It doesn't have friction or anything or wind resistance. So it could just keep going. Think about these gas particles. Why don't they slow down? Are they experiencing wind resistance? No. Because wind resistance is the air, right? They are the air. They are traveling through empty space. So they just keep going until they hit something and then they bounce off. Oops. So the ideas in kinetic molecular theory, the first one is the size of a particle is negligibly small. Gas particles do have volume, but their volume is so small in comparison to the whole volume of the gas that it really doesn't matter at all. So we're assuming the gas particles have zero volume, even though they do have mass. It's just because there's so much empty space. So at STP, argon atoms would only occupy 0.01% of the gas volume. The rest of it's empty space. So if an argon atom was the size of a golf ball, the closest neighboring gas particle would be 4 feet away. You could fit a lot of golf balls in there in 4 feet, right? There's a lot of empty space. So the size of the particle doesn't matter. It's a little bit like went on a family vacation years ago and drove through Wyoming. Beautiful state. You know what the population of Wyoming is? It's about the size of Fresno, without Clovis, just Fresno. Not a lot of people in Wyoming. It's a big state. There's a lot of empty space, right? So if you think about the people of Wyoming, if they were all like really, really big guys, or if they were all little petite, tiny women, does it really matter in terms of the space they occupy in the state? No, it doesn't matter at all. Now, you get 10 people in an elevator. Now, does it matter what size those people are? It does, because the size of the people compared to the overall space they're occupying is significant. And that's what happens with solids and liquids. They're touchingly close. There's not a lot of space there, so the size of the particles matters. In a gas is mostly empty space, and so the size of the particle doesn't matter. Second idea is that the average kinetic energy of the gas particles is directly proportional to the temperature in kelvins. As you raise the temperature of the gas, the average speed of the particles increases. It's the average speed. Some of them are moving fast, some are moving slow, but there's an average. When you heat up a gas, when you raise the temperature, the average speed goes up, because adding heat, you're adding energy to the system, and how does that energy get absorbed? It gets absorbed by the particles increasing their kinetic energy, moving faster. Collisions occur. Collision of one particle with another or with the walls is completely elastic, meaning you don't lose energy. There's no loss of energy as heat or anything. They just bounce off. And so that's why they don't slow down over time. So this is more about the elastic collisions. So playing pool, you've got these balls and they're hard, right? And when they bounce into each other, when they collide, they keep moving. This is not completely elastic, but it's about the closest we can get in real life. So you've got two balls coming at each other. They bounce off of each other, right? The energy is transferred from one ball to the next. If you start with a stationary, like say that the number 6 ball is stationary, and you hit the cue ball at it. The cue ball is moving. When it hits number 6, what happens? Usually 6 moves off, and the cue ball almost stops, right? It transferred its energy to the other ball, but there wasn't much loss of energy. If you try to do that with lumps of clay, this is an inelastic collision. You roll those together, and they just go and stick to each other, right? There's no transfer, there's no exchange, there's no moving on. They just stop because all of their kinetic energy is lost, okay? So this is what the gas particles are doing. They're bouncing off the walls, literally. So the gas particles are constantly moving. They're striking the sides of the container. When they hit the side of the container, they exert a force on the container. Pressure is a force over an area. So gas particles hitting the walls are going to exert a pressure on the container. Now, each gas particle hitting, they're very tiny, right, is a little teeny tiny force. But they all add up, and they can add up to be a very significant pressure. We can explain Boyle's law. Kinetic molecular theory can be used to explain all of these laws. So Boyle's law said that the volume of a gas is inversely proportional to the pressure. So if we decrease the volume, we're forcing the molecules into a smaller space. When they're in a smaller space, they're going to run into the walls of the container more frequently, right? And that's going to increase the pressure. If you increase the volume, make the container much larger, particles are still moving, they're not going to bump into the container as often, and the pressure will go down. And that's what Boyle's law tells us. Boyle's law just says what happens. Kinetic molecular theory explains why it happens. Charles' law, we looked at the relationship between a gas and the temperature. The volume of a gas is directly proportional to the absolute temperature. And when we look at Charles' law, we keep the amount of gas the same, and we keep the pressure of the gas the same. So kinetic molecular theory says if we increase the temperature of a gas, the average speed, and thus the average kinetic energy of the particles increases. So we've increased the temperature. What happens to the number of collisions? It increases. The particles are moving faster. They're going to get across the container and have to collide with the wall more frequently. And not only that, but because they're moving faster, they're going to hit harder. And so the pressure, in order to be constant, the pressure would go up unless we allow the container to expand. If we want to keep the pressure constant, we have to increase the volume of the container so that you can spread the collisions out over a greater surface area. And so the volume of a gas is directly proportional to its absolute temperature. Avogadro's law said that the volume of a gas is directly proportional to the number of gas molecules. So if we increase the number of gas molecules in a container, we're going to increase the number of collisions, right? More particles, more collisions. If we need to keep the pressure constant, how can we do that? We have to increase the volume of the container. Dalton's law, the partial pressures. Total pressure is equal to the sum of the partial pressures of each of the gases. So, kinetic molecular theory, the particles are of negligible size. So if we're looking at helium or krypton, the atoms are significantly different in size, but both of them are insignificant compared to the volume of the whole gas because there's so much empty space. So the size doesn't matter. The collisions are elastic. The particles are not interacting with each other. They may hit each other, but they're just going to bounce off and go their own way. So each of the gases acts like it's the only gas in the container. They're each going to exert their own pressure. Particles of different masses are going to have the same average kinetic energy at a given temperature. But the way they do that is they don't travel at the same speed. So you've got the same average kinetic energy, so they're hitting the walls with the same amount of force over a unit area, same pressure. So the average kinetic energy is the same, the total pressure of the collisions is the same regardless of what gas it is. Any questions? The ideal gas law. The predictions made by kinetic molecular theory are consistent with the observations and the measurements of gases. This model does break down under certain conditions, and we'll look at that. But looking at where it breaks down helps us to understand even more about gases. So the average kinetic energy of gas molecules depends on the mass and the average velocity. So kinetic energy is equal to 1/2 the mass times the velocity squared. So if we've got particles of different sizes, if the masses are different, but the average kinetic energy is the same, the thing that must be different is the velocity. They must have different average velocities. URMS, that is a U, not a V. This is called the root mean square velocity. It's a special kind of average. We're not going to get hung up on what special kind of average it is, but it's an average, just not a regular one. It's close in value to just the plain old average. But the average kinetic energy of a gas is equal to 1/2. This would be the number of particles times their mass times this average velocity squared. So if we have a gas at a given temperature, a mixture, so you have some heavier and some lighter particles, the lighter particles are going to travel faster than the heavier ones on average. Because if the mass is large, the velocity has to be smaller and vice versa. So if you think about football players, is it the smaller football players or the really big football players that run faster? The small ones, right? The running backs, the receivers, they can run quickly because they're smaller. And you get the big linebackers, they may be stronger than the little guys, but they've just got so much bulk to move, they can't run as fast. So if that helps you remember, big gas particles move slow, small gas particles are fast. We can actually calculate the average speed, and it is related to the molar mass of the substance. So the root mean square velocity is equal to the square root of 3 times the ideal gas constant times the temperature, and that's got to be in Kelvin. And capital M here is the molar mass, but it needs to be in kilograms per mole in order for these units to work out. And we're going to use a different set of units on R, 8.134 joules per mole Kelvin instead of liter atmospheres per per mole Kelvin. So we could calculate the root mean square velocity of gaseous xenon atoms at 25 degrees Celsius. So the root mean square velocity is equal to the square root of 3 RT over capital M. So R, we're going to use different units, 8.314. That's joules per mole Kelvin. The temperature needs to be in Kelvin. It's 25 degrees Celsius. So we'll convert that to Kelvin and get 298.15 Kelvin. And then the molar mass. So we're talking about xenon atoms, periodic table 131.3. What's the unit on that? Grams per mole. We need this to be in kilograms per mole. So grams down here, kilograms up there. Kilo means 10 to the positive 3. So I've got kilo on top. I'm going to put what it means underneath. 1 kilogram is 1 times 10 to the third grams. My fingers are dry. I can't move the screen. So that's going to be 0.1313 kilograms per mole. So let's put all this in here. So we've got the number 3 times 8.314 joules per mole Kelvin times 298.15 Kelvin divided by 0.1313 kilograms per mole. And it's the square root of the whole mass. So we can do the numbers. On my calculator, I'm going to do square root, and then 3 times 8.314 times 298.15 divided by 0.1313 equals 237.9856. How many sig figs does that have? Should have 4, right? So that'll be right there. So 238.0. Now, what about those units? Well, let's see if we can cancel some things out. Cancels Kelvin. Kelvin cancels. And moles cancel. And then I'm left with joule, the square root of joules per kilogram. Well, joule is equal to, let's see. It's meters, kilogram meters squared per second squared. Divided by kilograms and the square root of this. So the kilograms cancel out. We get the square root of meters squared per second squared, which is meters per second. This is why the molar mass has to be in kilograms, because of what the joule means. Joule is a kilogram meter squared per second squared. Let me Any questions? So lighter particles move faster. Lighter particles also have broader distributions. So what this graph is showing us is the relative number of molecules with an indicated velocity. Here's the molecular velocities along the x-axis, and we're looking at different gases. So oxygen, nitrogen, water, helium, and hydrogen. And so we see, if you pick the maximum here as sort of the average speed of hydrogen molecules is faster than oxygen. And that's what that previous equation would tell us as well. But what the equation doesn't tell us is that the distribution for hydrogen is much wider, meaning there's a lot more variability in the velocities. And when you get to heavier and heavier gases, the distribution gets more narrow. We also see an effect on this distribution of temperature. As you increase the temperature of the gas, you increase its average velocity, but the distribution widens out again. So faster velocity, whether it's from temperature or from size of particles, is associated with a broader distribution. So you have, on average, you have faster particles, but if you look at the really high-speed particles, those are much faster. Not very many of them, but a few.